Hello everyone, I'm Ali Atajanov. I'm a freshman student at Bilkent University at the Department of Electrical and Electronics Engineering. Today I'm going to present to you my Physics 101 lab experiment. The title of the lab experiment is Analyzing Motion with Constant Acceleration, specifically of projectile motion. The first part of the experiment was aimed to analyze whether the angle of launch is going to affect the total flight time and the total displacement along y and x axes. The second part of the experiment was aimed to analyze whether adding additional mass is going to affect the projectile motion. We expected increasing the angle of launch is going to increase the total displacement along the y-axis. Also, we expected increasing the angle of launch is going to increase the total flight time. In the second part of the experiment, we expected adding additional mass is not going to affect the projectile motion. Now let me introduce you to the experimental setup. I conducted my lab experiment on an air table. I placed a wooden cube beneath a middle adjustment screw to give an air table a proper inclination angle. Additionally, as you can see from the photo, I placed a spring diagonally to one of the corners of an air table to use it as a launcher. In the first part of the experiment, I'm going to launch a puck at 30, 45, and 60 degrees, and on the second part of the experiment, I'm going to launch a puck with a Velcro tape attached to it in order to increase its mass, again at 30, 45, and 60 degree angles. I'm going to alter the angles of launch by altering the, the side lengths of adjacent sides of a spring. However, it is worth noting that while doing so, we need to know that the position where we have to place the puck in order to launch it changes. As you can see from these photos, the position changes. Now let's see the video demonstration of the lab experiment. As you can see from the video, the puck makes a perfect projectile motion, and these demonstrations were done only for the sake of demonstration, as I did not turn on the spark timer. And this is a demonstration with a Velcro tape. As you can see, even with a Velcro tape, it again makes a perfect projectile motion. As you can see from the dots on the paper, the puck made a perfect projectile motion. Now let me walk you through the procedure through which that I obtained the data. First of all, I measured the mass of the puck, which turned out to be 0.42 kilograms, and then I measured the mass of the Velcro tape, which turned out to be 0.0036 kilograms. And then I measured the horizontal and vertical displacement with a 30 centimeter ruler. And I set the spark timer to 15 milliseconds. I obtained the horizontal component of initial velocity by first measuring the horizontal distance between the first ideal dot to the next dot and then dividing it by 15 milliseconds. And I got the vertical component of the initial velocity by the same procedure. The reason I did not include the gravitational acceleration in calculating the vertical component of initial velocity is because the first time interval is quite small to be able to make a huge difference. And then I calculated the theoretical total time flight by multiplying the vertical component of the initial velocity by 2 and then dividing it by acceleration. And acceleration here turned out to be 1.372 meters per second squared. The reason is I inclined the air table in such a way that the sine theta gave me a value of 0.14. And then I calculated theoretical displacement along x-axis by multiplying the initial horizontal velocity with the theoretical total time flight. And this is the written version of what I just explained. The first two graphs show that as the launch angle increased from 30 to 60 degrees, both the time of flight and the maximum vertical height increased, which agrees with the projectile motion theory. The curves of both masses nearly overlap, showing that the mass does not significantly affect the motion, and under the ideal conditions, it should not at all. The final graph compares the experimental and theoretical horizontal ranges and shows a strong linear relationship, again confirming the fundamental principles of kinematics. Some discrepancies between the experimental and theoretical values were observed. They can be attributed to the fact that the data might have been read from the ruler with some inaccuracy, the precision of the ruler itself, and the uncertainty in measuring the dot spacing. Additionally, it can be attributed to the residual friction, air resistance, or the possibility of the air table being not perfectly level. Overall, I was able to show that the fundamental principles of motion with constant acceleration accurately describe the real physical behavior if we account for errors. Thank you for watching. See you next time.